So this is some work that myself and some others listed here have done to look at spatial correlation. So as an outline for the talk, first of all, I'll give you a little bit of motivation as to why this work was initiated. And part of it involves calculating the spatial correlation between geological and geophysical features. And I'm not really sure what the best way of doing this, so I've come up with a couple of different proposals. One of them is linear fitting, and I'll explain to you how that's done with an example of gravity data. And then I'll illustrate it on the Chibougamau traverse, where it gives okay results, but not necessarily that definitive. And finally, on a bigger data set, the Metal Earth traverses, it gives a little bit more definitive results. And the second method is auto and cross correlation techniques, and I'll just touch on those as well too. And finally, I'll talk a little bit about some of the implications for crustal evolution and talk about some future work that might be interesting. So this is the motivation here. This started off as some work done by my student. This is an interpretation of a seismic section that Amir Malachi made. And on here, you'll notice, hang on, I'll just turn on my pointer. You'll notice a couple of highs in the mid-crust interface. So one here, another one here, another one here, some here as well too. And you notice that there are felsic plutons associated with many of these mid-crust highs. This high here is associated with the Chibougamau pluton. This one here is associated with two buried plutons that were interpreted from the gravity data. And there's another one here that's associated with a pluton as well too. This slide here was shown at the Partners and Advisory Board meeting last time we had one. And I also noticed a mid-crust high here on the old lithoprobe data set, which you can see here. And it turns out that this is also associated with a felsic pluton. And this is another slide from that same partners meeting more than a year ago. Here's a high in the mid-crust, another one here, another one, another one, another one. And you can see that there are, in many cases, felsic plutons associated with each of these mid-crust highs. So this is an interesting spatial correlation, but that's really a qualitative result. I wanted to try and quantify this in some way. So one way that you can do that is by doing linear fitting. So I'll describe that process here. Let's take an example of some gravity data. So this is gravity data from the Chibougamau area, and the light browns are lows. And you can see there's another low here and another low here. There's a subtle one here. There's another one here, and one here. So there's a number of gravity lows, and each one has been associated with the CMP number, which is a number associated with the location along the seismic traverse here. And you can look at the geology data as well, and you notice that there is a felsic pluton here, which roughly corresponds with this location. This location here has felsic plutons on either side. There's a bit of a felsic pluton here. Maybe you could associate it with this position. This is the Chibougamau pluton, which would be associated with that CMP number. There's another pluton up here, and there's a pluton here. But there are also some felsic rocks that might also have a gravity low that aren't plutons. Okay, so these are the locations. This is the CMP number along the seismic traverse, and the red spikes are where there are felsic batholiths, 1, 2, 3, 4, 5, 6, 7. And the black spikes are where there are gravity lows. And we expect that a felsic batholiths will have a gravity low, and you can see indeed that very often there are felsic batholiths that are associated with gravity lows, sometimes displaced by a little, as you can see here. But there are also gravity lows that don't have any associated batholiths. And those gravity lows might be associated with other geological features like felsic metasediments, for example, or successor basins. So what I've done on this plot is I've looked at each felsic batholith location, and I've looked for the closest gravity low. And if they aligned exactly, then they'd plot on this straight line with a slope of 1. And you can see that in some cases, they're off by a little bit. And in this case, I've looked at each of the gravity lows and looked to find the closest associated felsic batholith. And in that case, they don't plot as closely to a straight line. That's because the gravity lows don't cause felsic batholiths, but felsic batholiths are likely to cause gravity lows. And so generally what I do is I look for a feature that might cause something and then look for the closest associated feature. You'll notice as well too that I'm putting the root mean squared deviation. That's the deviation of those points from the straight line fit. So that's a measure of the misfit. If I look for the felsic ultramafics and the closest associated gravity lows, I get a poor fit. And we expect that because we don't expect mafics and ultramafics to have gravity lows because those are dense rocks. So this RMS deviation is a good example of one where we wouldn't expect to get a good fit, and so this is a poor fit. And here we have gravity lows and the closest associated mafic or ultramafic, and we don't expect gravity lows to cause ultramafics, and so here we see a very poor fit and a large root mean squared deviation. So let's apply that method now to seeing whether or not there's a correlation between the felsic batholiths that I've already showed you and these mid-crust highs that I have pointed out before. And not only am I looking for mid-crust highs like this one, I'm also looking for breaks in the mid-crust because this is a place where there is often a high anyway. Here's another break and there's a relative high. Here's a break here, and on this side there's a high, and similarly here. So highs occur on their own, such as you see here, or at these mid-crust structures. So what I've done is I've plotted the location of the mid-crust highs and the mid-crust structures along the bottom here in blue and red, and on the top in black I've plotted the felsic batholith locations. So if you look at this, you can see that the batholith locations in some cases align with the red features, such as here and here, although there's also a blue one. But in this case, the felsic batholiths align with the blue features, which are the crustal structures. These mid-crust highs here don't have any felsic batholiths associated with them. So if I look for the mid-crust high locations and look for the closest associated felsic batholith, then I get something that does look like a straight line, but there's a few places where it doesn't, and the root mean squared deviation for this data set is about 9 in this case. If I look for the crustal structures and the closest associated felsic batholiths, I get 5 points, which give a better fit, smaller root mean squared deviation. And if I look for an example where I don't expect a good fit, that's where I'm looking for the mafic and ultramafics that have been mapped on the geology and the closest associated felsic batholiths. I get quite a bit of scatter and a very poor root mean square deviation. So this is an example of what might be random data, and anything that has a better root mean square deviation than this might be a good correlation. But frankly, we're only looking at 5 points in this particular case. So that's not a particularly good data set to look at with just 5 points. We need more points to get a more robust estimate of what the fits and the root mean squared deviation are. So what I've done is I've expanded that process that I just showed you for Chibougamau, and I've done it for all the Metal Earth traverses. So all 13 traverses in the initial campaign. I interpreted the seismic data. I looked for the mid-crust highs and the mid-crust structures, and I looked for the closest associated felsic batholiths and mafic and ultramafics. And when I find the locations of the mid-crust highs and the closest associated felsic batholiths, I get something that does look pretty much like it's plodding along a straight line, and the scatter is not too bad. The root mean square deviation is about 5 kilometers or so, which is sort of roughly the uncertainty that I have in where I pick the mid-crust highs and the mid-crust structures, and also the felsic batholiths and the deviations that might occur from a geological context. So that's okay, that root mean square deviation. As well, the crustal structures and the closest associated felsic batholiths also plot on a straight line, except for a couple of locations here. And the root mean square deviation is about 5 kilometers as well. For the sample that I don't expect a good agreement, the mafic, ultramafic locations and the associated felsic batholiths, or the nearby felsic batholiths, show a lot of scatter, 8.8 kilometers in that case. So that's the sort of scatter we would expect if it was random, because felsic batholiths and ultramafics aren't necessarily going to be associated with each other in any coherent way. So anything that's got an RMS deviation that's lower than 8.8, like the previous two examples I showed you, is probably not random. So that's the conclusion from that linear fitting method. I also tried it using the auto and cross correlation methods, which is another spatial correlation technique that geophysicists use. And essentially what they do is they correlate the positions of one feature with the positions of another using a convolution algorithm. And if you correlate two features that do agree exactly, then you should get zero away from the zero lag position, and you should get a big spike at the zero lag position. And that's sort of what you see here when I correlate felsic with felsic. So you notice that we're at the noise level, and then at zero lag, boom, we get this big spike. So felsic do agree with felsic, and elsewhere they don't. So the noise levels are of the order of 3,000 in this case. And the next one, and I'm having trouble reading this, but just let me try and move that. Yeah. So here I'm correlating felsic with mafic. And you can see that I don't want to get a correlation here at zero lag. And you see that I don't. I get something around 2,500. But off here at about -7 kilometers and here at +7 kilometers, I do get a bit of a spike. And what that's telling you is that on average, felsic features are about 7 kilometers away from mafic features. And that seems about right. You would expect that if I told you, you wouldn't be surprised by that. And now on the next slide, I show the correlation between felsic and the mid-crust highs. And around zero, I do get a peak. And I get a background noise at around 2,500. So there is a little bit of a peak. There seems to be a correlation between felsic batholiths and mid-crust highs. And this shows the correlation between felsic batholiths and mid-crust structures. And you can see that there is a bit of a peak here, but it's barely above the background on this side, but a little bit above the background on the other side. So these auto and cross correlation techniques are consistent with the conclusions that I came to previously, that felsic batholiths are spatially associated with mid-crust highs and mid-crust structures. So what are the implications for that for crustal evolution? So here I've drawn a schematic mid-crust high, and here's a schematic mid-crust structure. In this particular case, it's a thrust, but it doesn't have to be a thrust. It could also be a normal fault. And I've drawn some felsic batholiths that are associated with these, and how might these be associated with them? And in this particular case, I'm arguing that in the Archean, the rocks were a lot hotter. Molten rocks would have been closer to the surface, and these felsic material here might have been molten. They are less dense than the surrounding rocks, and so they would be buoyant and they'd want to move up. So they'd move in the upwards direction, as you see here and here, and these two would converge at this location. They're feeling the pressure of other ones wanting to get up on either side of them. They don't have anywhere to go, and so they'll break through any breaks in the crust here and work their way up. And in this case, you can see I've got them going up directly, but if there's some structure, then they might get pushed off to the side and be deflected along that structure. So conceivably, they could be up to 5 kilometers away. And in this case, we've got a mid-crust structure. Here we've got this molten felsic material, and there's a structure here that it can move up. So it can either move up directly, or at some point it can start to move up vertically, so that it might be up to 5 kilometers away from this mid-crust structural location. So that's just a schematic diagram to give you some sort of implications for what's going on here. Now, the work that I've done is sort of preliminary. It's just a start to this work. There's lots of other stuff that could be done. So, for example, I've just looked for the felsic plutons. I haven't distinguished between the syntectonic plutons and the late plutons. Perhaps if this work was redone, then we could get some sort of idea of whether these different types of plutons might be related to different types of structures, the highs or the mid-crust structures. And that might help us to understand the timing of what's going on in the Archean. We could also subdivide up the mid-crust structures themselves. So, for example, some of them might be associated with successor basins, and some might not be associated with successor basins. So in that case, that might help us to understand the metallogenic importance of those particular structures. And also we could do this study on the basis of the different greenstone belts. So what I've observed might be a little bit different in the Abitibi from the Western Superior, or it might even be different from the Chibougamau, because the Chibougamau greenstone belt is a little different from other greenstone belts in the Abitibi, because Chibougamau has less fold structures. So all of these subdivisions decrease the amount of data that I have when I'm doing these analyses, and reduces the confidence that we have in the results. So one way that we could bring back the confidence level is by including more seismic data in the analysis. So, for example, we could also extend this not just to the Metal Earth seismic data, but also to the lithoprobe seismic data. So those are all ideas that I think might be interesting for students to work on in the future. And that's the end. I thought I had some conclusions, but that's good enough for now.
Great. Thank you very much, Richard. And are there any questions for Richard?
Richard Alireza speaking from Uppsala. I have two questions for you, and I pasted it in the chat room, but I repeat them again. I missed to see your criteria for gravity highs and lows, and if you pick them from gridded data or these were from point observations. That's my first question. The second one is, well, I guess you touched on it. In many of these crustal scale seismic data we look at, what you interpret crustal highs are rather structurals than anything related to plutons. So they're rather shear zones or fold zones. Can you comment? You mentioned in the conclusion that you're going to look into this a bit, but aren't you not kind of risking that you're mixing more of a structural highs with plutons?
Okay, so in answer to the first question, I just looked at the gridded data. The big obvious features you can see on the grids, sure, there are more subtle features that you might see on the profiles, but those subtle features are often small anyway. So the big ones that you can see on the grids were the ones that I used for picking the lows. I didn't necessarily have to have the lows right on the profile. The lows could be off to the side, right? So as are the felsic batholiths off to the side. So that was the reason why I used the gridded data. In answer to your questions about the shear zones and the significance of these crustal highs, I didn't really try and put too much interpretation into what the highs were, because that's putting a sort of an interpretation bias into it. I just identified what looked to me to be a high on the seismic data. And what I really used was the place where the data goes from not showing a lot of reflectors to starting to show more laterally coherent, quasi-layered reflectors. Does that sort of answer your question?
Yeah, no, that's right, clear. Yeah. Could you also comment on what was the criteria for gravity lows and highs? How did you decide what is low, how much is low, how much is high?
Just if it was obvious on the gravity map.
Okay, thank you.
Okay, do we have any other questions? One in the chat room, Richard from Bruno. Could those crustal highs be the roof of a large batholith with plutons at surface being related?
Yeah, I guess they could. Yeah, I mean, in some sense, that's a sort of an extreme case of what I was talking about.
Okay, very interesting.
Yeah, Richard, Desmond here. Could the correlation of the felsic plutons with the crustal highs that you see in the seismic sections, could that be because the plutons have higher velocities, which might tend to pull up the reflections from the mid-crust?
Yeah, that's a good question. That's exactly the same question that a reviewer asked in the review process. And the answer to the question is that the velocities aren't that different. So I don't think it could be a pull-up effect.
Okay, and one other question. You picked the location of felsic plutons from the geology maps. Are you actually able to see any of them in the seismic sections, or do they not image very well?
The plutons don't necessarily image that well in the seismic data, in the ones that I looked at. And often the plutons are off to the side as well, too. So, you know, I would pick a felsic pluton off to the side of the seismic profile, because, you know, maybe it extends underneath the profile at depth. And even if it does extend, maybe the structure that caused it might extend underneath the seismic profile. So, yeah, does that answer your question?
Yeah, thank you.
Thank you very much, Richard. We've come to the end of the Partner Advisory Board meeting. You know, thanks everyone for your attention. And as I mentioned earlier, you know, the main reason we do this is so, you know, we can catch up with our colleagues and we can understand what our colleagues are doing. But we also like to get some feedback, you know, whether it's positive, negative, constructive feedback is always welcome. So if you have any, please send it off to me, and we'll take it into account going forward.